Welcome to Still Science Lab. Tonight, we explore a question at the edge of modern physics. What if one tiny particle could reveal that reality is deeper than our current theories? Not a particle we can see with our eyes, not a visible object drifting through space, but a faint signal in a detector, a missing piece in an equation, a brief trace left behind by something so small and elusive that it may point beyond the known rules of matter itself. Deep underground, far below the noise of the surface, some of the most sensitive instruments ever built wait in darkness. They are shielded by rock, silence, and distance from ordinary interference. Above them, cities move, weather changes, engines run, and cosmic rays strike the atmosphere. But below, inside carefully controlled chambers, physicists are listening for something almost impossibly subtle. A tiny flash of light, a recoil in an atom, a whisper of energy where no ordinary signal should be. The machines do not look for wonder in the way human beings do. They do not look up at the stars. They do not ask questions in words. They wait for disturbances, small deviations, unexpected patterns, evidence that something passed through matter and left behind the faintest possible signature. Elsewhere, in long tunnels beneath the ground, particles are accelerated to extreme energies and driven into collision. For a fraction of a moment, energy becomes a tool for opening the structure of reality. Known particles smash together. New particles may appear and vanish almost instantly. Detectors surrounding the collision record what remains. Tracks, flashes, energy deposits, decay patterns, and missing momentum. The original event is gone almost as soon as it happens, but the evidence remains. That is how particle physics often works. Scientists rarely see the thing itself. They reconstruct it from what it leaves behind. A particle may exist for less than a heartbeat. It may decay before it can travel any meaningful distance. It may interact so weakly that most of the universe passes through it unnoticed. But if it leaves the right kind of trace, and if that trace appears again and again, it can become the beginning of a new understanding. And sometimes the trace does not fit. That is where the story becomes dangerous in the scientific sense. A particle that could change everything is not a magical object. It is not a fantasy ingredient inserted into physics to make reality more dramatic. It is not proof that the universe has broken its own laws. In science, a particle that could change everything means something more precise and more powerful. It means a particle that does not fit the known rules, a signal that should not appear where it appears, a behavior that does not match the predictions, a possible new ingredient in the universe's hidden structure. Modern physics already has a remarkably successful map of particles and forces. It describes ordinary matter with extraordinary precision. It tells us how electrons behave, how quarks form protons and neutrons, how forces are carried, how particles transform, and how the Higgs field helps give mass to many of the particles we know. This framework has survived decades of testing. It is not fragile. It is not guesswork. It is one of the strongest achievements in the history of science. But it is not complete. That incompleteness is not a failure. It is a clue. The universe contains dark matter, yet the known particles do not explain what dark matter is. The universe is expanding faster over time, yet the nature of dark energy remains unresolved. Gravity shapes galaxies, black holes, and space-time, yet it does not fit neatly into the same quantum framework as the other forces. Neutrinos have masses that suggest deeper structure. Matter survived the early universe in a way that still demands explanation. The known theory works beautifully, but the universe is larger than the known theory. This is why one tiny particle can matter so much. A new particle would not merely add another name to a list. It could reveal a hidden force, It could connect ordinary matter to dark matter. It could point toward a deeper symmetry beneath the particles we already know. It could show that the standard model is not the final layer of physics, but one visible surface of a larger structure. A single particle can be a doorway, not because it is large, because it is connected to a rule. In physics, particles are not just little objects. They are tied to fields, interactions, and patterns of law. Discovering a new particle can mean discovering a new field. A new field can mean a new kind of interaction. A new interaction can change the way we understand matter, energy, and the early universe. That is why the search is so patient. Physicists are not simply hunting for something strange. They are trying to distinguish real strangeness from noise. Most unusual signals do not become discoveries. Many vanish with more data. Some turn out to be background effects. Some are caused by detectors behaving in unexpected ways. Some are ordinary physics wearing an unfamiliar mask. Science knows this. That is why it is careful. A signal must survive skepticism before it becomes real in the scientific sense. It must appear repeatedly. It must grow stronger with more evidence. It must be checked against every known explanation. It must be seen, if possible, by independent experiments. A particle that could change everything has to earn that power, but even before certainty, the possibility is enough to make physicists listen. Because the history of science is filled with moments when small anomalies revealed deeper worlds. A tiny mismatch in prediction, a missing energy balance, a strange decay, an unexpected track, a pattern too persistent to ignore. At first, these things can look like mistakes. Later, they can become revolutions. Not always, but sometimes. And when they do, reality expands. The particle at the edge of reality may not be dramatic in appearance. It may not glow. It may not tear open space. It may not announce itself as the answer to dark matter or the key to a hidden force. It may begin as a statistical excess, a bump in collision data, a rare event in a detector, or an absence where energy seems to have escaped unseen. It may be recognized only because the known theory predicted something slightly different. That is the subtle power of modern physics. We can notice when reality disagrees by a little, and sometimes a little disagreement matters more than a spectacular display. Because the universe often hides its deepest truths behind precision. The most important clue may not be loud. It may be a faint deviation, repeated enough times to become impossible to dismiss. It may be a number that refuses to settle where it should. It may be a trace that quietly says, "Your map is incomplete." This is the suspense at the heart of the search. What if the signal is nothing? What if it fades? What if it is noise? Then science learns, corrects, and moves on. But what if it stays? What if the particle is real? Then a small event inside a detector could reach far beyond the laboratory. It could connect to the invisible matter shaping galaxies. It could point back to particles created in the early universe. It could suggest that ordinary matter is only one sector of a much larger physical world. It could reveal that the forces we know are not the only forces nature allows. The smallest thing could change the largest story. That is why this question is not only technical, it is existential in a quiet, grounded way. Everything we are made of belongs to the known structure of matter. The atoms in the body, the air in the lungs, the light entering the eye, the chemistry of thought. All of it depends on particles and fields. If there is a deeper layer beneath them, then reality itself has been carrying hidden structure all along. A new particle would not mean the world we know is false. It would mean the world we know is partial. The table would still be solid. The stars would still burn. The equations that work would still work within their domain. But behind them, there may be another layer of explanation. another grammar beneath the language of matter, another set of rules shaping the visible universe from the shadows. This is not fantasy, it is the frontier, the edge where careful measurement meets deep uncertainty, where detectors listen in silence, where accelerators recreate violent moments of creation, where physicists study traces too small for human senses, hoping that one of them might belong to something nature has kept hidden until now. What if one tiny particle could reveal that reality is deeper than our current theories? The honest answer is that we do not know. But physics has learned to respect small clues, because sometimes the universe changes our understandings, not by showing us something enormous, but by leaving behind the faintest possible trace of something new. A particle at the edge of reality, a signal almost lost in the noise, a quiet mark in the data, and perhaps behind it a hidden structure beneath everything we thought we knew. A single particle can change physics because a particle is rarely just a thing. In everyday language, the word particle sounds small and simple. It suggests a tiny object, a speck of matter, a little piece of the universe added to the inventory. One more item in a catalogue, one more name to memorize, one more entry in a table. But in modern physics, a particle can mean much more than that. A particle can be the visible sign of an invisible field. It can be the messenger of a force. It can be evidence of a hidden symmetry. It can reveal that matter follows a deeper rule than the one scientists previously understood. When physicists discover a new particle, they are often not only discovering a new object, they are discovering a new way the universe is organized. That is why a single particle can reshape science. Particles are not isolated marbles floating through empty space. They belong to frameworks. They carry properties that matter deeply: mass, charge, spin, lifetime, and the ways they interact with other particles. Those properties are not random labels. They tell us where the particle fits in the deeper architecture of physical law. A particle with a certain charge tells us which forces it feels. A particle with a certain mass tells us something about how it relates to fields. A particle that decays in a particular way reveals what transformations nature allows. A particle that should not exist under current theories may reveal that the theory is not complete. This is the crucial point. A new particle is not just another piece of matter. It can be evidence of a new rule. History has shown this again and again. Some particle discoveries confirmed that theories were on the right track. Others revealed forces that were previously hidden. Others helped explain why atoms have structure, why matter is stable, why stars shine, and why the universe behaves the way it does at the smallest scales. Before many of these discoveries, the universe seemed simpler. Then a new particle appeared, or was predicted, or left traces in data, and the map had to expand. A particle can act like a signature. It tells physicists that something deeper is present, in the same way smoke can reveal fire, or a footprint can reveal an animal that has already passed. A particle can reveal a field, a force, or a symmetry that cannot be seen directly. This is especially important because modern physics is built from fields. Every known particle is associated with an underlying quantum field. What we call a particle is often a localized excitation of that field, a discrete event in something that extends through space. The electron is connected to the electron field. Photons are connected to the electromagnetic field. Other particles are connected to other fields. So discovering a new particle may mean discovering a new field. And a new field is not a minor addition. It can change the foundation. A field can shape what particles exist. It can determine how they interact. It can influence the early universe. It can connect visible matter to invisible matter. It can change the way physicists understand the vacuum, forces, and the structure beneath ordinary reality. This is why the discovery of one particle can be larger than the particle itself. The particle is the clue. The field is the deeper story. Forces also enter through particles. In quantum physics, interactions are often described through carrier particles or through fields whose excitations mediate forces. The particles associated with a force are not merely passengers in the universe. They are part of the way influence moves between systems. Discovering a particle connected to a new interaction would mean discovering that nature has a way of communicating with itself that we did not know about. That possibility is enormous. The known forces already shape everything familiar. Electromagnetism gives atoms their structure and makes chemistry possible. The strong force holds atomic nuclei together. The weak force allows certain particles to transform and plays a crucial role in stellar processes. Gravity shapes planets, stars, galaxies, and space-time itself. If a new particle revealed a hidden force, it would not simply add a footnote to physics. It could reveal a new grammar of reality. Because forces are not just things that happen to particles. Forces define relationships. They determine what can bind, what can repel, what can decay, what can transform, and what can remain stable. A new force would mean new relationships were possible in nature. It would mean the universe had been using a rule that our current theories had not yet named. This is why particle discoveries are so powerful. They can expose hidden symmetries. A symmetry in physics is not only visual balance, it is a deep principle about what remains unchanged when something is transformed. Symmetries help explain conservation laws, particle families, force structures, and why certain interactions are allowed while others are forbidden. When a new particle appears, it may fit into a symmetry pattern, or it may break an expected pattern. Either case can be revealing. A particle that completes a pattern can confirm a theory. A particle that violates a pattern can force a new theory. Both outcomes matter. This is what makes a new particle different from a new asteroid, a new moon, or a new type of mineral. Those discoveries may be important, but they do not always rewrite the laws beneath everything. A particle can. Because particles sit close to the foundation of physical explanation. They are not just things in the universe. They are expressions of the rules that make a universe possible. If the rules change at that level, the meaning spreads outward. Atoms, stars, galaxies, the early universe, the matter in our bodies, the invisible mass surrounding galaxies, the balance between matter and antimatter. All of these may depend on particle physics. That is why physicists take even tiny anomalies seriously. A faint signal in a detector may seem insignificant compared with the scale of planets and galaxies. But if the signal belongs to a new particle, it may connect to questions far larger than itself. It might explain why dark matter exists. It might reveal why neutrinos behave strangely. It might point to a hidden sector of particles that barely interact with ordinary matter. It might help explain why the universe contains matter at all. It might show that the standard model is only one layer of a deeper framework. A single particle can become a bridge between the microscopic and the cosmic. This is one of the great surprises of modern science. The smallest entities can carry the largest implications. A particle that exists for less than a fraction of a second inside an accelerator may help explain conditions moments after the birth of the universe. A particle that barely interacts with matter today may account for the gravitational structure of galaxies. A particle that appears as a small deviation in a detector may reveal that fields beyond the known ones are present everywhere. The universe hides scale inside detail. The tiny can speak for the vast. Past discoveries have taught this lesson repeatedly. Some particles were predicted before they were found, and their discovery confirmed that the mathematical structure behind them was real. Others were detected as missing energy or unusual decay patterns, revealing invisible participants in physical processes. Some helped show that matter was not elementary in the way people once believed. Others confirmed that fields and symmetries were not just elegant ideas, but physical features of nature. Each discovery changed the map, not always by destroying the old map, often by deepening it. That distinction matters. A new particle does not usually mean everything before it was wrong. Physics rarely advances by throwing away every successful idea. More often, it discovers the limits of a theory. The older theory remains true within its domain, but the new discovery reveals a larger domain beyond it. Classical physics still works for bridges, planets, and ordinary machines. Relativity expands the picture at high speeds and strong gravity. Quantum mechanics expands it at small scales. A future discovery may expand the standard model without erasing the enormous success it already has. This is how science grows, not by replacing truth with falsehood, but by replacing a partial truth with a deeper one. A new particle could be exactly that kind of deeper truth. It could show that the known particles are not the complete alphabet of matter. It could show that the known forces are not the complete grammar of interaction. It could show that the visible universe is connected to hidden fields or hidden sectors that have influenced cosmic history from the beginning. And the strange part is that such a discovery might begin almost silently, not with a dramatic explosion, not with a glowing object, but with data, a bump in a graph, a decay happening slightly too often, a missing energy pattern, a tiny disturbance in an underground detector, a result that refuses to match expectation. This is why particle physics is so patient. Scientists are searching for rules inside traces. They are trying to decide whether a small signal is noise, known physics, or something new. Most hints disappear. Most anomalies become lessons in caution. But every once in a while, the signal stays. And when it stays, the universe changes shape in the human mind. A new particle becomes a new question. What field produced it? What force does it feel? Why does it have this mass? Why does it decay this way? Was it present in the early universe? Does it still exist in space today? Is it connected to dark matter? Does it point to a symmetry we have not yet understood? A particle discovery is not the end of the story. It is the beginning of a deeper investigation. That is why one particle can change physics. Because one particle can reveal that reality has another layer. It can show that the known rules are not final. It can connect the behavior of matter in a laboratory to the hidden architecture of the cosmos. A new particle is not just another item in the universe's inventory. It can be evidence of a new rule, and in physics, a new rule is one of the most powerful discoveries possible. The standard model is the closest thing physics has to a map of ordinary matter. Not a map of planets, stars, or galaxies, but of the ingredients beneath them. The hidden architecture below chemistry, the structure behind atoms. The framework that tells us what the visible universe is made of, how its smallest known parts behave, and how those parts interact through the forces that shape matter at the deepest levels we can test. It is not a simple theory, but its central idea can be stated plainly. The standard model describes the known elementary particles and three of the fundamental forces of nature. It includes the particles that make up matter, the particles that carry forces, and the Higgs field, which helps explain why many particles have mass. It is the best tested framework ever built for the microscopic world. And for ordinary matter, it works with astonishing precision. Everything familiar begins inside this map: the atoms in a human body, the carbon in living cells, the oxygen in the air, the silicon in a computer chip, the light emitted by a star, the chemistry of water, the behavior of electrons in metal, the nuclear reactions that power the sun. Beneath all of it are particles and fields behaving according to rules described with extraordinary success by the Standard Model. At the center are matter particles. These include quarks and leptons. Quarks combine to form protons and neutrons, the particles inside atomic nuclei. Electrons, one kind of lepton, surround those nuclei and allow atoms to form, bond, and build the chemistry of the world. Neutrinos, also leptons, pass through matter with ghost-like ease, produced in nuclear reactions, radioactive processes, and cosmic events across the universe. These particles are not arranged randomly. They come in families. They have charges, masses, spins, and interaction patterns. They obey deep mathematical rules. They are not tiny pieces thrown into the universe without structure. They belong to a framework of symmetry and law. Then there are the force carriers. Matter does not simply exist. It interacts. It binds, scatters, transforms, and radiates. The Standard Model explains these interactions through quantum fields and their associated particles. The electromagnetic force is carried by photons. It governs light, electricity, magnetism, atomic structure, chemistry, and almost everything we directly feel in everyday life. When your hand touches a table, what you experience as solidity is rooted largely in electromagnetic interactions and quantum rules between atoms. The strong force is connected to gluons. It binds quarks together inside protons and neutrons, and it is ultimately responsible for holding atomic nuclei together. Without it, the nuclei of atoms would not exist. Without nuclei, there would be no ordinary matter as we know it. The weak force is carried by heavy force particles and allows certain particles to transform into others. It plays a crucial role in radioactive decay and in the nuclear processes that allow stars to shine. It is subtle compared with electromagnetism in everyday experience, but it is essential to the physics of matter and the life cycles of stars. Together, these forces describe an enormous range of reality. But one force is missing: gravity. The Standard Model does not include gravity in the same way it includes the electromagnetic, strong, and weak forces. Gravity is described by general relativity, a separate and incredibly successful theory in which mass and energy curve space-time. For planets, stars, black holes, and the expansion of the universe, general relativity is indispensable. But gravity does not fit neatly into the quantum framework of the Standard Model. That absence matters. It is one of the first signs that the map, powerful as it is, may not be complete. Still, within its domain, the Standard Model is astonishing. It has predicted experimental results with a level of accuracy that is difficult to overstate. In particle accelerators, scientists collide particles at enormous energies, then compare the debris with theoretical predictions. Again and again, the Standard Model gives the correct patterns. It tells physicists what particles should appear, how often certain interactions should occur, and what traces should be left inside detectors. It does not merely describe what was already known. It predicted. It guided. It survived. One of its greatest achievements was the prediction and discovery of the Higgs boson, the particle associated with the Higgs field. The Higgs field fills space, and many particles acquire mass through their interaction with it. This was not a decorative idea added to physics. It was a crucial missing piece in explaining why the Standard Model could work the way it does. When the Higgs boson was finally detected, it was not just the discovery of another particle. It was the confirmation of a deep mechanism, a sign that the invisible field proposed by theory had a measurable trace in reality. That is how the Standard Model often works. It connects abstract mathematics to physical evidence. It takes invisible fields and turns them into predictions. It describes particles that may exist for less than a fraction of a second, then identifies them through the patterns they leave behind. It is one of the great triumphs of human reasoning, but triumph is not finality. A good map can be accurate and unfinished. The Standard Model explains ordinary matter beautifully, but the universe is not made only of ordinary matter. The stars, planets, gas, dust, and bodies we see appear to be only a small fraction of the total cosmic content. Galaxies rotate as if surrounded by invisible mass. Clusters of galaxies bend light more strongly than visible matter can explain. The large-scale structure of the universe points towards something unseen. Dark matter. The Standard Model does not tell us what dark matter is. That alone is a major clue that something lies beyond the map. Then, there is dark energy, the name given to whatever is driving the accelerated expansion of the universe. It dominates the large-scale fate of the cosmos, yet its nature remains deeply mysterious. The Standard Model does not provide a satisfying explanation for it. Neutrinos add another puzzle. They exist within the Standard Model, but their masses and identity-changing behavior suggest that the simplest version of the theory is incomplete. These ghost-like particles may be pointing toward physics that lies beyond the known structure, and there is the great asymmetry of existence itself. The early universe should have produced matter and antimatter in nearly equal amounts. Yet the universe today is filled mostly with matter. Something tipped the balance. The Standard Model contains some ingredients that distinguish matter from antimatter, but not enough to fully explain why anything material survived to become galaxies, planets, and life. These are not small gaps. They are windows. They show that the Standard Model is powerful, but not the final story. This is why physicists search for particles beyond it. A new particle could be the first sign of the missing layer. It might connect to dark matter. It might reveal a hidden force. It might explain neutrino masses. It might point toward a deeper symmetry. It might show that the visible world is only one sector of a larger physical reality. A particle that does not fit the Standard Model would not erase everything the theory has achieved. That is important. If a new particle is discovered, atoms will not stop behaving as atoms. Electrons will not lose their properties. The Standard Model will not become useless. Its predictions will still work across the domain where they have been tested. But the discovery would mean the theory is part of a larger structure, just as Newton's laws remain useful within everyday speeds and weak gravity. Even though Einstein revealed a deeper picture, the Standard Model may remain a brilliant approximation of known particle physics while still being incomplete at the frontier. This is how science deepens, not by declaring every old idea wrong, but by discovering where each idea ends. The Standard Model gives us a universe of extraordinary order. It tells us that matter is not arbitrary, that particles belong to patterns, that forces arise from fields, that the smallest known components of reality follow rules precise enough to predict experiments across decades. But beyond that order, there is shadow, dark matter, dark energy, gravity, neutrino masses, the matter-antimatter imbalance, the unknown physics of the earliest universe, the possibility of hidden sectors and undiscovered forces. The map is bright where it has been tested, but the edges remain dark. And that darkness is not ignorance without direction. It is the place where the next discovery may appear, a strange signal in a detector, a missing energy event, a particle decay that happens too often, a tiny deviation from prediction, a new particle that refuses to belong to the known catalogue. Any of these could become the first clue that the Standard Model, for all its power, is not the final language of matter. That is, the suspense. The Standard Model is one of the most successful theories humans have ever created. It explains the visible structure of ordinary reality with extraordinary accuracy, but the universe is still holding back part of the stories. And somewhere beyond the particles we know, beyond the forces already named, there may be another layer of law waiting to be found. The most powerful maps in science are not only valuable because of what they show, they are valuable because of what they leave blank. The standard model shows us an extraordinary amount. It describes the known particles of matter, the force carriers, that govern their interaction, the Higgs field that helps explain why many particles have mass. It gives structure to the microscopic world. It explains atoms, light, nuclear processes, particle collisions, and the foundations of ordinary matter with remarkable accuracy. But when physicists look at the universe as a whole, they find something unsettling. The known universe works, but it does not explain itself completely. There are missing pieces in the map, not small errors at the edges of a finished picture, but deep absences. Places where observation says something is there, yet the standard model cannot fully tell us what it is. Places where the equations work beautifully in one domain, but stop short of explaining the whole. The first missing piece is dark matter. Galaxies do not move as if they contain only the matter we can see. Stars orbit their galactic centers too quickly. Clusters of galaxies behave as if they are held together by far more mass than visible stars and gas can provide. Light from distant objects bends around massive structures more strongly than ordinary matter alone can explain. Something is adding gravity, something vast, something unseen. We call it dark matter, but the name is not an answer. It is a label for a mystery. Dark matter does not shine like stars. It does not absorb or emit light in the ordinary way. It does not appear in telescopes as glowing gas or dust. We know it mostly by what it does gravitationally. And the standard model does not contain a clear dark matter particle. That is one of the greatest clues that known particle physics may be incomplete. If dark matter is made of particles, then those particles may belong to a hidden sector of physics, a part of reality that interacts weakly with ordinary matter, perhaps almost invisibly, while still shaping galaxies through gravity. Such particles might be passing through Earth right now without touching almost anything. They might fill the galaxy, silent and unseen, forming a cosmic structure we can measure but not directly identify. A new particle could change that. It could be dark matter itself, or it could be a mediator, a bridge between ordinary matter and the dark sector. It could explain why galaxies hold together, why cosmic structure formed the way it did, and why the visible universe is only part of the full reality. This is why dark matter is not merely an astronomical puzzle. It may be a particle physics puzzle written across the sky. The second missing piece is dark energy. The universe is expanding, and that expansion is accelerating. Distant galaxies are moving away from one another in a pattern that suggests space itself is being driven apart by something we do not fully understand. The name dark energy points to this unknown cause. But again, the name is not an explanation. Dark energy is not simply a particle waiting in a detector. It may be connected to the energy of empty space, to the structure of gravity, or to something even deeper. It dominates the large-scale behavior of the cosmos. Yet its physical nature remains one of the most difficult questions in science. The standard model includes quantum fields, and quantum fields have vacuum behavior. But connecting those ideas to the observed acceleration of the universe creates problems so severe that physicists know something is missing in our understanding. The vacuum is not simple. Empty space may not be empty in the way common sense suggests, and the energy associated with it may be one of the deepest unsolved mysteries in physics. Then there is gravity. Gravity is everywhere in the universe. It shapes planets, stars, galaxies, black holes, and the expansion of space itself. Our best theory of gravity is general relativity, which describes gravity not as an ordinary force, but as the curvature of space-time caused by mass and energy. General relativity is profoundly successful. The standard model is profoundly successful. But they are not united. The standard model is a quantum framework. General relativity is a theory of space-time geometry. Each speaks a different language. In most situations, that separation is manageable. Quantum physics dominates the very small. Gravity dominates the very large. But there are places where both must matter. The centers of black holes, the earliest moments of the universe, and any regime where spacetime itself may have quantum structure. There, our current map becomes incomplete. A deeper theory of quantum gravity is still missing, and any new particle, field, or hidden interaction might offer clues about how gravity connects to the quantum world. Perhaps gravity is not simply another force added to the standard model. Perhaps spacetime itself emerges from deeper quantum information. Perhaps the missing theory requires new ingredients we have not yet detected. Gap is not a failure. It is a frontier. Neutrinos add another quiet mystery. They are among the most elusive particles known. They pass through matter with extraordinary ease, crossing planets, bodies, and detectors, as if the material world were almost transparent. The standard model includes neutrinos, but their behavior has revealed something unexpected. They have mass, and they can change identity as they travel. This was not part of the simplest original picture. Neutrino mass suggests that something deeper is happening. Perhaps there are additional kinds of neutrinos that interact even more weakly. Perhaps neutrino masses arise from mechanisms beyond the standard model. Perhaps these ghost-like particles are pointing toward physics, hidden almost completely from ordinary detection. They are small clues, but small clues matter. In physics, a tiny mass can imply a vast structure. A rare interaction can reveal a hidden law. A particle that barely touches matter can still change the map of reality. Then there is the mystery of why matter exists at all. The early universe should have produced matter and antimatter in nearly equal amounts. Matter and antimatter are opposites in a deep physical sense. When they meet, they can annihilate into radiation. If the universe had made them in perfectly equal quantities, almost everything might have vanished into light, leaving behind a cosmos with very little matter to form stars, planets, or life. But that is not what happened. Matter survived. Galaxies exist. Stars exist. Planets exist. We exist. Something in the early universe tipped the balance. The standard model contains some differences between matter and antimatter, but not enough to fully explain the universe we observe. There must have been some process, some asymmetry, some rule or interaction that allowed matter to outlast antimatter. This is not a minor question. It is the reason there is a material universe to study. A new particle could be part of the answer. It might have existed in the early universe and decayed in a way that favored matter. It might belong to a hidden sector that influenced the balance. It might reveal a deeper symmetry and a deeper breaking of that symmetry. It might help explain why the universe did not erase itself in its first moments. The missing pieces are connected by a common theme. The standard model explains what ordinary matter does, but it does not explain why the universe contains all the ingredients it appears to contain. It does not explain the invisible mass-shaping galaxies. It does not explain the accelerating expansion of space. It does not unite gravity with quantum mechanics. It does not fully explain neutrino masses. It does not explain why matter survived over antimatter. The theory is powerful, but the universe keeps pointing beyond it. This is why physicists do not treat the gaps as embarrassments. They treat them as clues. A gap in a successful theory is not the same as a collapse of the theory. It is a signal that the theory has a domain. It works here, with extraordinary precision, but something lies beyond its reach. That is how science has always expanded. Classical physics worked until light, atoms, and high speeds revealed its limits. Newton's gravity worked until relativity revealed a deeper geometry. Early atomic models worked until quantum mechanics revealed the structure beneath chemistry. The Standard Model may be the same kind of achievement, deeply true within its tested territory, but not the final explanation of reality. This is where the possibility of a new particle becomes so important. A particle beyond the Standard Model could be connected to dark matter. It could reveal a hidden force. It could explain neutrino masses. It could help solve the matter-antimatter imbalance. It could show that ordinary matter is only one visible island in a larger ocean of fields and interactions. The particle itself might be almost invisible. It might not shine. It might not carry electric charge. It might interact so weakly that detecting it requires years of patience and instruments buried deep underground. But if it exists, it could be one of the missing keys, not because it is large, because it belongs to a larger rule. A hidden sector of physics may be especially important. This idea suggests that there could be particles and forces beyond the Standard Model that interact only faintly with the particles we know. They may be difficult to detect, not because they are far away, but because they do not communicate strongly with ordinary matter. They could be all around us and still hidden. That is a strange thought. The visible universe may not be the entire physical universe. There may be fields we have not mapped, particles we have not identified, interactions we have not named. We may be living inside one layer of a deeper structure, aware only of the parts that couple strongly enough to light, atoms, and detectors. A new particle could be the first message from that hidden layer. The known universe works. Atoms hold together, stars shine, chemistry builds complexity, gravity gathers galaxies, light carries information across space. The Standard Model explains much of the microscopic machinery behind ordinary matter. But the known universe does not explain itself completely. It leaves evidence of invisible mass. It expands under an unknown influence. It contains gravity without a complete quantum description. It holds neutrinos that do not fit the simplest expectations. It exists as matter, even though antimatter should have nearly erased it. These gaps are not empty. They are shaped like questions, and perhaps somewhere inside one of those questions, a new particle is waiting. Not as a final answer, but as the first clue that the map of reality is larger than the part we have already drawn. Searching for an unknown particle is like investigating a crime scene where the suspect may have vanished before the evidence was even recorded. There is no tiny object sitting under a microscope, no glowing speck of matter waiting to be isolated, no particle with a label attached to it, announcing that it belongs to a hidden layer of physics. At the smallest scales, nature does not usually give scientists the thing itself. It gives them traces, a flash of light, a curved track, a burst of energy, a pattern of decay, a missing piece in the balance. A disturbance so small that it would mean nothing unless the experiment had been designed to notice exactly that kind of silence. This is how invisible particles are found, not by seeing them directly, but by reconstructing what must have happened from the evidence they leave behind. In particle accelerators, scientists begin by creating extreme conditions. Known particles are accelerated to enormous energies and collided. For a brief instant, the collision region becomes a tiny arena where energy can transform into matter, where fields can be excited, and where particles too unstable to exist in ordinary conditions may appear for less than a fraction of a second. Then they are gone. Some decay almost immediately, Some transform into familiar particles. Some escape without interacting strongly enough to be detected. Some leave only an imbalance, a clue that something carried energy or momentum away from the scene. The detector does not capture the whole event like a camera capturing a photograph. It records consequences. It records where energy was deposited, which particles passed through, which layers, how tracks curved in magnetic fields, where showers of secondary particles formed, and whether the total visible energy adds up the way it should. Primitives. From these fragments, scientists sieve backward. They ask what combination of known particles could have produced the pattern. They calculate what the standard model predicts. They compare billions of events against expectation. They look for rare structures inside the noise, a small excess, a strange distribution, a decay that happens too often, or a region where energy seems to disappear. This is the forensic logic of particle physics. The particle may vanish instantly, but it leaves evidence behind. Some evidence appears as collision products. If an unknown particle is created in a high-energy collision, it may decay into particles that detectors can recognize. Those final particles become the fragments of the invisible event. By measuring their energies, directions, and identities, physicists can infer whether they might have come from a parent particle that existed only briefly. It is like hearing an echo and reconstructing the shape of a room, or finding ashes and reconstructing the fire. The original particle is no longer present, but the final state carries memory. Sometimes the evidence appears as a mysterious bump in data. When scientists plot the results of many collisions, known physics often creates smooth backgrounds and predictable patterns. But if a new particle is produced and decays in a specific way, it may create a small rise above the expected background, a concentration of events around a particular energy. At first, such a bump is only a suspicion. It might be real, it might be noise, it might be a statistical fluctuation, it might be a known process that was not modeled perfectly. So scientists wait for more data. If the bump fades, the mystery dissolves. If it grows sharper, the tension increases. The question becomes harder to ignore. Is this only chance, or is something new briefly appearing and disappearing inside the collisions? Other searches rely on missing energy. This is one of the strangest tools in modern physics. If all visible particles in an event are measured, their total energy and momentum should balance according to conservation laws. But sometimes something appears to be missing. The visible debris does not account for everything. That absence can be evidence. A particle may have escaped the detector without leaving a direct trace. Neutrinos do this regularly. They interact so weakly that they often pass through matter almost untouched. If an unknown particle behaves in a similar way, it may reveal itself not by what it deposits, but by what it removes from the visible accounting. In physics, a missing piece can be as important as a visible one. An invisible particle can announce itself by making the event incomplete. Then there are decay patterns. Particles are not only identified by what they are, but by what they become. Unstable particles decay according to rules. Some decays are common, others are rare, some are forbidden, or highly suppressed by known physics. If a particle decays in a way that happens more often than predicted, or if a known particle produces an unexpected final state, physicists begin to ask whether another influence is present. Maybe a hidden particle participated. Maybe a new force altered the process. Maybe the known theory is missing a subtle contribution. The evidence may be only a shift in probability, but at the frontier of physics, probability matters. A tiny change in a decay rate can point toward particles too heavy, too rare, or too hidden to observe directly. This is called an indirect search. The new particle does not need to appear as a visible object. It may influence known particles from behind the scenes, leaving a small distortion in the pattern of ordinary events. Like a planet discovered through the wobble of a star, an unknown particle may be inferred through the behavior of particles we already know. Other experiments take a quieter approach. Instead of creating particles in collisions, they wait. Deep underground, shielded from cosmic rays and surface radiation, detectors search for rare interactions from particles passing through Earth. This is especially important for dark matter searches. If dark matter is made of particles, those particles may be flowing through the galaxy and through our bodies constantly. But if they barely interact with ordinary matter, almost all of them pass unnoticed. So scientists build enormous, quiet instruments. They cool materials. They purify detectors. They surround them with shielding. They place them beneath mountains or deep inside mines. Then they wait for one tiny disturbance, a nucleus recoiling, a faint flash of light, a small amount of charge, a vibration, a signal that might mean an invisible particle finally touched ordinary matter. The challenge is almost absurd in its difficulty. The detector must be sensitive enough to notice an extremely rare event, but disciplined enough to reject countless false ones. Natural radioactivity, cosmic rays, electronic noise, impurities, and ordinary background processes can all imitate the signal. The experiment must become quiet enough for the universe's faintest whisper to stand out. The silence is engineered. Every material is chosen carefully. Every background is measured. Every possible source of contamination is questioned. Because the particle being searched for may interact so rarely that a false signal could mislead years of work. This is why unknown particle searches take patience. Science at this scale is not only about building powerful machines, it is about building trustworthy silence. It is about knowing the ordinary so precisely that the extraordinary can be recognized. A new particle cannot simply be strange. It has to be strange in the right way. It has to survive comparison with known physics. It has to appear more often than chance allows. It has to fit a pattern that can be tested. It has to remain after detector effects, background noise, calibration errors, and statistical accidents have been examined. Most hints disappear. That is part of the process. A strange signal may look exciting in early data, then fade as more events are collected. A suspected excess may turn out to be a fluctuation. A mysterious disturbance may come from a background source no one fully understood at first. A missing energy pattern may be explained by known particles escaping detection. This is not failure, it is filtration. Science protects itself by trying to disprove its own excitement. The rare signal that survives that process becomes powerful. It becomes more than a hint. It becomes evidence. And if independent experiments begin to see reseated signs, the case grows stronger. A particle moves from possibility to candidate, from candidate to discovery, only after surviving doubt. That doubt is essential, because the consequences are enormous. Finding a new particle could mean discovering a new field. It could reveal a hidden force. It could connect ordinary matter to dark matter. It could explain something about the early universe. It could show that the standard model, powerful as it is only one layer of a deeper structure. But before it can do any of that, it has to be real. And reality at the edge of measurement is difficult to separate from noise. This is what gives the search its tension. Scientists are not only looking for something small, they are looking for something that may barely touch the world we are made of. A particle that might pass through entire planets without leaving a mark. A particle that may appear only in rare collisions. A particle that may exist only briefly before decaying into familiar debris. a particle whose presence may be written only as a missing number in the conservation of energy. It is a search for the almost absent, and yet that almost absent thing could explain something enormous. Dark matter may be invisible, but it shapes galaxies. Neutrinos barely interact, but they carry information from stars and supernovae. Short-lived particles vanish quickly, but they reveal the fields and forces that govern matter. The hidden can be powerful. The faint can be fundamental. That is why particle detectors are, in a sense, instruments of humility. They remind us that the universe does not reveal itself only through brightness, size, or force. Sometimes it reveals itself through a discrepancy, through a tiny recoil, through a flash in darkness, through the fact that an event does not balance unless something unseen was there. The unknown particle may never be seen directly, but if it exists, it does not need to be seen in the ordinary sense. It only needs to leave a trace nature cannot explain any other way. A track, a decay, a flash, a missing energy signature, a disturbance in a detector buried beneath the earth, a pattern that appears again and again until doubt begins to turn into recognition. This is how scientists search for the hidden ingredients of reality, not by demanding that the universe become visible, but by learning to read the marks left by things too small, too brief, or too silent for human senses to notice. And somewhere inside those marks, the next particle that changes physics may already be waiting. The first sign of a particle that does not fit is rarely a dramatic discovery. It usually begins as a disturbance, a small bump in collision data, a rare decay that appears slightly more often than expected, a missing energy pattern that refuses to balance cleanly, a faint signal inside a detector where known physics predicted only background, nothing loud enough at first to rewrite reality, nothing certain enough to announce as a new law of nature, just a trace, a question, a place where the map and the measurement no longer align perfectly. This is how the most important discoveries often begin, not with certainty, but with tension. A known theory makes a prediction, an experiment measures the world. For a while, the two agree beautifully. Then, somewhere inside the data, a small pattern appears that does not behave like the rest. Most of the time, that pattern disappears. It turns out to be noise, a statistical fluctuation, a detector effect, a background process that was underestimated. Science is full of almost discoveries, and most of them are absorbed back into the ordinary world after more careful analysis. But sometimes the signal remains, and when it remains, physicists begin to ask a deeper question. What kind of particle would leave this trace? The possible particle does not need to be visible in any ordinary sense. It may not travel far enough to leave a long track. It may decay almost instantly into known particles. It may carry no electric charge, making it nearly invisible to many detectors. It may interact so weakly that it escapes the experiment, leaving only missing energy behind. It may belong to a hidden sector of physics, a part of reality that barely communicates with ordinary matter. That is why this kind of discovery is so difficult. The particle may not appear as an object. It may appear as a pattern. A bump in a graph can be one form of evidence. In high-energy collisions, physicists know what ordinary processes should produce. They predict how many events should appear at different energies and in different channels. If the data rises above expectation in one narrow region, it may suggest that a short-lived particle was created and then decayed into visible fragments. The particle itself is gone, but its mass and behavior may be inferred from what it became. A rare decay can be another clue. Known particles decay according to rules. Some decay paths are common, some are rare. Some should happen only with extreme suppression. If a decay occurs too often, or with a pattern that does not fit the standard model, It may suggest that an unknown particle is influencing the process from behind the scenes. The new particle may never appear directly. Its presence may be felt as a subtle distortion in the behavior of particles we already know. Missing energy can be even stranger. Detectors are built around conservation laws. When particles collide, the visible products should account for the energy and momentum that went into the event. If they do not, something may have escaped unseen. Neutrinos do this. A dark matter candidate might do this. A hidden particle could pass through detector layers without interacting, leaving behind only an imbalance. In that case, absence becomes evidence. The missing part of the event becomes the clue. This is why a particle that does not fit is so powerful. It would not just be another small object added to the universe. It would be a sign that the known rules are incomplete. Known particles have specific patterns. They have masses, charges, spins, lifetimes, and interaction behaviors. They belong to the structure of the Standard Model, one of the most successful scientific frameworks ever created. A new particle outside that structure would demand an explanation. Why does it have this mass? Why does it interact this way? Why has it remained hidden? Does it belong to a new field? Does it carry a new force? Does it connect ordinary matter to dark matter? Was it present in the early universe? Could it help explain why the universe contains matter at all? These questions matter because particle physics is not only a catalogue, it is a system of rules. Each known particle fits into a larger architecture. Electrons, quarks, neutrinos, force carriers, and the Higgs boson are not random pieces scattered through reality. They are organized by symmetries, fields, and interactions. So when something appears outside the known catalogue, the issue is not simply that scientists have found one more thing. The issue is that the rules may have another layer. A particle with no electric charge, very weak interactions, and long stability could point toward dark matter. A particle that appears in rare decays could suggest a hidden force. A particle too heavy to exist in ordinary conditions, but briefly produced in a collider, could reveal physics that mattered when the universe was extremely young. A particle that interacts through an unknown field could show that the visible world is only one part of a larger physical system. That is the suspense. The particle may be tiny, but the implication may be enormous. A hidden particle could explain why galaxies hold together. Across the universe, stars move as if more mass exists than telescopes can see. Clusters of galaxies bend light more strongly than visible matter can account for. The cosmic web seems shaped by something gravitationally present, but optically invisible. If this missing mass is made of particles, then a signal in a detector on Earth could connect directly to the structure of galaxies. A particle could also point back to the early universe. In the first moments after the beginning, energy was high enough for particles and interactions that may be impossible to produce naturally today. Some particles may have vanished as the universe cooled. Others may have survived as relics. Some may have helped create the imbalance between matter and antimatter. Some may have shaped the formation of cosmic structure long before the first stars existed. A tiny signal now could be the fossil of an ancient rule. This is why physicists are cautious, but also deeply interested. A particle that does not fit could be nothing, or it could be the first visible edge of something vast. The caution is essential. A mysterious bump is not automatically a new particle. A rare decay is not automatically new physics. A missing energy event is not automatically dark matter. Every possible ordinary explanation must be tested. Backgrounds must be understood. Detectors must be calibrated. Statistics must strengthen. Independent measurements must confirm the pattern. Science does not accept a reality-changing particle because the idea is exciting. It accepts it only if the evidence survives. That survival is what turns mystery into discovery. At first, the possible particle exists only in uncertainty. It lives in the space between noise and law. The data hints at it, but does not yet prove it. The theory struggles to contain it, but does not yet yield. The signal may fade, sharpen, or transform into something unexpected. This is the fragile stage of discovery, when reality has not yet spoken clearly. And yet, even this stage matters. It shows where physicists should look. It reveals where the standard model may be under pressure. It tells scientists which measurements need more precision, which backgrounds need deeper understanding, and which theories may deserve attention. Even an anomaly that disappears can improve the map, but an anomaly that remains can open a door. If the particle is real, it would not mean the standard model is useless. The known particles would still behave as they do. Atoms would still form. Chemistry would still work. The theory would still explain the enormous range of phenomena it already explains. But the standard model would no longer be the whole story. It would become one layer of a deeper framework. That is how physics often changes. Not by erasing the past, but by revealing that the past was part of a larger truth. Newton's laws did not vanish when relativity arrived. Classical physics did not vanish when quantum mechanics emerged. The old theories remained powerful within their domains, while the new theories showed why those domains had limits. A new particle could do the same. It could show that the visible world is only a subset of physical reality. It could reveal hidden matter, hidden fields, or hidden forces. It could connect laboratory physics to cosmic mysteries that have remained unsolved for decades. It could suggest that beneath mass, charge, spin, and interaction, there are symmetries we have not yet recognized. This is why the particle that does not fit feels so important. It stands at the boundary between what is known and what may be deeper. It is not a fantasy object. It is not a miracle. It is not proof that reality has broken. It is a possible signal that our description of reality is incomplete. And that possibility is enough to make physicists listen. Because the universe often reveals itself indirectly. It does not always show the hidden structure directly. It leaves effects. It leaves patterns. It leaves missing energy, unexpected decays, and small statistical excesses that become meaningful only after years of careful measurement. The particle that could change everything may not arrive with drama. It may arrive as a whisper inside data, a signal too small for the senses, but too persistent for physics to ignore, a particle outside the catalogue, a trace beyond the standard model, a quiet indication that matter, force, space, and the early universe may all be connected to a deeper layer still waiting to be named. A new particle would be extraordinary. But the deeper question is not only whether the particle exists. The deeper question is what it means. In modern physics, particles are not isolated curiosities. They are connected to fields, forces, and rules. A particle can be a piece of matter, but it can also be a messenger. It can carry an interaction from one system to another. It can reveal that nature has a way of connecting things that we had not previously recognized. That is why a new particle could be more than a new entry in a catalogue. It could be evidence of a hidden force. Forces are the grammar of the universe. They determine how particles relate, how matter binds, how energy moves, and how structures form. Without forces, particles would be like letters scattered without language. They might exist, but they would not combine into atoms, stars, chemistry, or life. If particles are the alphabet of reality, forces are the grammar. They tell the letters how to form words. They tell matter how to become structure. They tell the universe what kinds of relationships are allowed. The forces we know already shape everything familiar. Electromagnetism governs light, electricity, magnetism, chemistry, and the structure of atoms. It is responsible for the behavior of electrons, the bonds between molecules, and much of what we experience as touch, color, and material form. The strong force binds quarks together inside protons and neutrons, and ultimately holds atomic nuclei together. Without it, the core of matter would fall apart. No stable nuclei, no atoms beyond the simplest possibilities, no heavy elements, no planets made of rock and metal. The weak force allows certain particles to transform into others. It plays a crucial role in radioactive decay and in the nuclear processes that allow stars to shine. It is subtle compared with the forces we feel directly, but it is essential to the evolution of matter. And gravity shapes the universe on the largest scales. It gathers gas into stars, stars into galaxies, galaxies into clusters, and curves the path of light around massive objects. It governs planetary orbits, black holes, and the expanding structure of the cosmos. These forces are not just background effects. They are the rules by which the universe becomes organized, but the known forces may not be the whole story. That possibility is one of the most important reasons physicists search for particles beyond the standard model. A new particle might not simply be a new form of matter. It might be the carrier of an interaction we have not yet discovered. It might be a messenger from a hidden sector of physics, a part of reality that does not communicate strongly with ordinary matter. A hidden force would not necessarily appear in everyday life. It might not move objects in a visible way. It might not affect chemistry under normal conditions. It might not produce light, heat, or pressure we can easily detect. If it interacts only weakly with the particles we know, then it could have remained unnoticed through all of human history. But unnoticed does not mean non-existent. The universe may contain interactions that are quiet to us, because we are made of ordinary matter, sensitive mainly to ordinary forces. We see through electromagnetism. We touch through electromagnetism. Our atoms are held together through known interactions. Our bodies evolved inside the narrow domain where familiar forces dominate. A hidden force could operate mostly elsewhere. It might act on dark matter. It might connect particles in a hidden sector. It might influence rare decays, missing energy events, or tiny deviations in precision experiments. It might have shaped the early universe before becoming almost invisible today. This is where dark matter becomes especially important. Dark matter appears to exist because of its gravity. Galaxies rotate as if they contain far more mass than visible stars, and gas can explain. Clusters of galaxies bend light as if surrounded by invisible matter. The cosmic web seems to have formed under the influence of something that does not shine, but gravity may not be dark matter's only interaction. Perhaps dark matter feels a hidden force. Perhaps it has its own particles, its own fields, its own internal structure. Perhaps ordinary matter sees only the gravitational shadow of a richer dark world. If so, a new particle detected in a laboratory could be a bridge between our visible sector and that hidden one. It might be a messenger, not a messenger carrying words, but a carrier of interaction. A particle that allows two sectors of reality to speak faintly to each other. This idea must be handled carefully. A new particle would not automatically prove a hidden force. A strange signal may still be noise, background, detector behavior, or misunderstood known physics. Even if a new particle were confirmed, scientists would still need to measure its properties, its interactions, and its role in a larger theory. But the possibility is powerful because particles and forces are so deeply linked. In quantum physics, forces are described through fields and interactions. Some force-carrying particles are familiar parts of the standard model. Photons carry electromagnetism. Gluons are associated with the strong force. Heavy particles mediate the weak force. These are not merely objects moving around. They are expressions of how fields interact and how influence is transmitted. So, if a new particle appeared with the right behavior, physicists would ask whether it belongs to a new field. And if it belongs to a new field, they would ask whether that field creates a new interaction. A hidden force could be very weak, or very short-ranged, or mostly connected to particles we cannot see directly. It might reveal itself only through rare processes. A known particle might decay in a slightly unexpected way. A collision might produce missing energy more often than predicted. An underground detector might record tiny disturbances that do not fit known backgrounds. A precision measurement might disagree with theory by a small but persistent amount. Such clues would not be dramatic to the senses, but in physics, a small deviation can be a doorway. The discovery of a hidden force would change the meaning of the universe's inventory. It would show that the particles we know are not only missing ingredients, but perhaps missing relationships. It would suggest that reality has a grammar beyond the one described by current theories. And grammar matters more than vocabulary alone. A new particle is like a new letter. A new force is like a new rule for how letters can combine. With a new grammar, the same universe can become more meaningful. Patterns that once looked accidental may become necessary. Mysteries that seemed unrelated may become connected. Dark matter, rare decays, early universe physics, and particle anomalies might all become parts of a deeper structure. This does not mean one discovery would answer everything. Science rarely works that way. A hidden force would raise new questions as quickly as it solved old ones. Why is the force hidden? What particles feel it? Why is it weak or difficult to detect? Did it matter in the early universe? Does it still shape dark matter today? Can it be unified with known forces? Does it point toward a deeper symmetry? A new force would not end physics. It would expand it. There is a long pattern in science where new forces and interactions reveal deeper layers of order. Electricity and magnetism were once separate phenomena, then became unified as electromagnetism. Nuclear forces revealed that atoms contained inner structures far beyond chemistry. The weak force showed that particles could transform in ways that changed our understanding of matter. Gravity, through relativity, became geometry itself. Each step did not merely add a new phenomenon. It changed the framework. A hidden force would do the same. It would tell us that nature has another way of connecting physical systems, another way for fields to influence one another, another route by which matter, visible or invisible, can organize itself. And if this force is connected to dark matter, the implications become cosmic. The dark matter around galaxies might not be a simple cloud of passive invisible mass. It might have structure, interactions, and history. It may have influenced how galaxies formed, how matter gathered, or how the early universe evolved. A hidden force could shape the unseen architecture behind the visible cosmos. That is the scale hidden inside the question. A particle discovered in a detector on Earth could reveal a force acting in the dark regions of galaxies. A faint anomaly in laboratory data could point toward interactions that shaped the cosmic web. The smallest signal could carry information about the largest structures. Still, the responsible answer remains cautious. Could a new particle reveal a hidden force? Yes, in principle. Would every new particle do that? No. Would every strange signal prove it? Absolutely not. The signal must survive. The particle must be confirmed. Its interactions must be measured. Competing explanations must be ruled out. Theoretical models must make predictions that can be tested. A hidden force must earn its place in physics through evidence, not excitement. But if evidence points that way, the discovery would be profound. It would mean the universe has been communicating through rules we had not yet learned to hear. It would mean ordinary matter is not the full stage of physical reality. It would mean there may be sectors of nature that are real, structured, and active, yet almost invisible to the particles and forces that make up our bodies. This is what makes the idea so mysterious without needing exaggeration. The hidden force, if it exists, would not be supernatural. It would be natural in the deepest sense. A law of nature not yet recognized, a grammar not yet translated, a relationship written into reality before any mind existed to discover it. And perhaps that is why one new particle could feel so important. Because it might not be alone. It might be the first visible member of a larger hidden family, the first message from a field we have not mapped, the first trace of an interaction that has been shaping the universe quietly from behind the scenes. A new particle might reveal a hidden force. A hidden force might reveal a hidden sector. A hidden sector might reveal that the visible universe is only one layer of a deeper physical order. Not a fantasy universe, not a magical dimension, but a real part of nature connected to ours by faint interactions and patient evidence. If particles are the alphabet of reality, forces are the grammar, and somewhere beyond the known letters and rules, physics may be waiting for the first sign of a new sentence. The smallest thing in nature may explain the largest structures in the universe. That is one of the deepest reversals in modern physics. When we look at galaxies, clusters, and the cosmic web, the scale feels almost beyond thought. Hundreds of billions of stars bound together by gravity, vast filaments of matter stretching across space, empty-looking voids separating luminous islands of galaxies, light traveling for billions of years before reaching us. The universe, at that scale, seems like a story of size, distance, and gravity. But the reason those structures exist may depend on particles too small to see. A single kind of hidden particle, barely interacting with ordinary matter, could help explain why galaxies formed the way they did. A particle created in the extreme heat of the early universe could still be shaping cosmic structure today. A tiny difference in how particles and antiparticles behaved may be the reason matter survived at all. The very large may be written in the language of the very small. Dark matter is the clearest bridge between particle physics and cosmology. Across the universe, galaxies behave as if they contain far more mass than we can observe directly. Stars orbit galactic centers too quickly. Galaxy clusters hold together too strongly. Light from distant galaxies bends around invisible gravitational sources. The cosmic web itself seems to have grown under the influence of unseen matter that does not shine, does not absorb light, and does not announce itself through ordinary electromagnetic signals. Something is there, something massive, something hidden. We call it dark matter, but the name is not a solution. It is a placeholder for a mystery. It tells us what the unseen substance does, not what it is. Dark matter pulls through gravity. It shapes motion. It guides the formation of structure, but it does not reveal itself in the way ordinary matter does. If dark matter is made of particles, then those particles must be very different from the particles that make up atoms, stars, planets, and bodies. They may not carry electric charge. They may not emit or absorb light. They may pass through ordinary matter almost untouched. They may be all around us, flowing through the galaxy, crossing Earth, passing through our bodies, and leaving no noticeable trace. A barely interacting particle could be the answer, or it could be a bridge to something deeper. This is where hidden sectors become important. A hidden sector is a possible part of physics that contains particles and forces beyond the standard model, but interacts only faintly with ordinary matter. It may be real and active, yet nearly invisible to us, because our detectors, bodies, and telescopes are mostly sensitive to familiar forces. In that view, dark matter may not be a single simple particle. It could be part of a richer, hidden world, with its own interactions, fields, and history. Ordinary matter may be only one visible sector of a larger physical reality. Dark matter may be another sector, present everywhere in the universe, but communicating with us mainly through gravity and, perhaps through rare, faint interactions. A new particle could be the messenger between those sectors. It might not be dark matter itself. It might be a mediator, a particle that allows ordinary matter and hidden matter to interact slightly. It might appear in a detector as missing energy, a rare decay, or a small deviation from expectation. It might be created briefly in high-energy collisions, then vanish into invisible states. It might help explain why dark matter has remained hidden for so long, while still leaving its gravitational signature across the cosmos. That is why a tiny signal inside a laboratory can matter to cosmology. A particle detector on Earth may be searching not only for a new ingredient of matter, but for the invisible structure behind galaxies. The early universe gives this connection even greater depth. Before stars existed, before galaxies gathered, before planets formed, the universe was hot, dense, and filled with particles, radiation, and quantum fields. The conditions were so extreme that particles too heavy or unstable to exist naturally today may have been common then. Interactions that are now rare may have shaped the entire future of the cosmos. A particle discovered now may be a fossil of that earlier reality. Not a fossil made of stone or bone, but a relic of physical law. Some particles may have been produced abundantly in the early universe, then survived as dark matter. As space expanded and cooled, others may have decayed away, but left behind consequences. An imbalance between matter and antimatter, a change in the formation of structure, or a hidden relationship between ordinary matter and a dark sector. The universe we see today may carry the memory of particles that existed when everything was young. One of the greatest mysteries from that early time is the survival of matter. In the beginning, matter and antimatter should have been created in nearly equal amounts. When matter meets antimatter, the two can annihilate into radiation. If the balance had been perfect, almost everything material could have disappeared, leaving behind a universe filled mostly with light and very little matter. But that did not happen. Matter remained. Stars formed, galaxies formed, planets formed, bodies formed. Some physical process must have tipped the balance. Something made matter slightly more abundant than antimatter. The known laws contain some asymmetries, but not enough to fully explain the universe as we observe it. A new particle could be part of that missing explanation. It may have behaved differently with matter and antimatter. It may have decayed in a way that favored matter by a tiny amount. It may have participated in interactions that were important only in the intense conditions of the early universe. A small imbalance at the particle level could have become the difference between a universe rich with matter and a universe almost empty of structure. This is the emotional scale of particle physics. A tiny asymmetry can become existence. A microscopic rule can become galaxies. A hidden particle can become the reason there are stars at all. Galaxy formation also depends on the unseen. After the early universe cooled, tiny variations in density began to grow under gravity. These variations were small at first, but over cosmic time, they became the seeds of structure. Dark matter played a crucial role because it could begin gathering gravitationally without being pushed around by light in the same way ordinary matter was. It formed invisible scaffolding. Ordinary gas later fell into those gravitational wells, cooled, condensed, and eventually formed stars and galaxies. Without dark matter, the universe would not look the way it does. Galaxies might have formed differently later, or not with the same structure. The cosmic web, that immense network of filaments and voids, may be the visible result of invisible matter shaping the growth of the universe from its earliest stages. If a new particle explains dark matter, then it explains part of the architecture of the cosmos. It explains not only what is missing, but why the universe has shape. That is why the search for hidden particles is not separate from astronomy. Particle physicists and cosmologists are often studying the same mystery from opposite directions. Telescopes map where dark matter must be. Particle detectors try to discover what dark matter is. Cosmological surveys measure the large-scale structure of the universe. Underground experiments wait for rare interactions. Colliders attempt to create hidden particles under controlled conditions. One field looks outward, the other looks inward. Both are asking what the universe is made of. A new particle could connect these searches. It could appear in collision data, influence rare decays, or leave missing energy in detectors. It could also match the behavior needed to form cosmic structure. The same particle that barely touches ordinary matter in a laboratory might be the invisible mass holding galaxies together. That would be a profound unification of scale. The small would explain the large. The hidden would explain the visible. The particle would explain the pattern. But the story must remain careful. A new particle signal does not automatically solve dark matter. Many possible particles could exist beyond the standard model without being dark matter. Some could be unstable. Some could interact too strongly or too weakly. Some could be unrelated to cosmic structure. The connection must be tested. The properties must match. The abundance must make sense. The particle must fit both laboratory evidence and cosmological observation. Science does not accept a cosmic explanation because it is beautiful. It accepts it when the evidence converges. Still, the possibility is powerful because the clues already point beyond the known map. Dark matter is real in its gravitational effects. The matter-antimatter imbalance is real in the existence of galaxies and stars. The early universe must have contained physical processes that shaped what came later. The standard model explains much, but not enough to close the story. A hidden particle could be one of the missing pieces. It could tell us why the universe contains invisible mass. It could reveal a hidden sector behind ordinary matter. It could help explain how matter survived. It could show how the early universe produced the conditions from which galaxies emerged. It could connect the smallest measurable events to the largest observable structures. This is why particle physics is not only about particles. It is about history, cosmic history, the story of how fields cooled, symmetries changed, particles appeared and disappeared, matter survived, gravity amplified tiny differences, and galaxies eventually formed. Every star in the night sky belongs to that history. Every atom in the body belongs to it. The matter in our hands exists because early universe physics allowed matter to remain, and the invisible matter around galaxies may be made of particles still waiting to be identified. There is something humbling in this. Human beings stand at a middle scale. We are too large to see particles directly, and too small to feel the galaxy as a whole. Yet by building detectors and telescopes, we can connect both directions. We can study the faintest traces of hidden particles and the largest structures in space, then ask whether they are part of the same answer. The universe may be telling one story in two languages. In the sky, through gravity and galaxies. In the laboratory, through tracks, decays, and missing energy. The task of physics is to translate between them. If the particle exists, it may not look important. It may be quiet, weakly interacting, nearly invisible, a tiny signal buried in data, but its role could be enormous. It may have helped shape the early universe. It may still surround galaxies today. It may be part of the hidden architecture, holding the visible cosmos together. The smallest thing in nature may explain the largest structures in the universe. A particle too faint to see may explain why galaxies hold. A decay too rare to notice easily may explain why matter survived. A hidden sector, barely connected to us, may explain why the universe is larger, darker, and more layered than ordinary matter alone can reveal. And if that connection is real, then one tiny particle would not merely change particle physics. It would change the story of the universe itself. The most difficult question in a moment of scientific excitement is not what if the signal is real. It is what if the signal disappears. That possibility has to remain in the room. It has to stand beside every bold headline, every whispered theory, every suggestion that a new particle may have been found at the edge of known physics. Because in science, a signal that could change everything must first survive the possibility that it changes nothing. Many exciting signals have vanished with more data. A strange bump appears in collision results, then smooths out when the experiment runs longer. A rare decay looks unusual, then returns to the predicted rate. A tiny excess seems to point toward a hidden particle, then fades into ordinary statistical noise. A detector records something unexpected, and for a while the question feels alive. Then the instrument is recalibrated, the background is better understood, the analysis improves, and the mystery dissolves. This is not failure. This is how science protects itself from false certainty. At the frontier of particle physics, the difference between discovery and illusion can be incredibly subtle. Science are often searching through enormous amounts of data, looking for events that may be rare, faint, and difficult to separate from background processes. The universe is full of ordinary things that can imitate extraordinary ones. A detector is not a perfect window into reality. It is a complex physical system built from materials, electronics, fields, timing systems, software, and assumptions that must all be understood with extreme care. A small error can look like a clue. A background process can look like new physics. A random fluctuation can look like a particle. This is why the first appearance of a strange signal is never the end of the story. It is the beginning of a test. The signal must be questioned from every direction. Scientists ask whether the detector behaved exactly as expected. They ask whether known particles could have produced the same pattern. They ask whether the calibration was stable. They ask whether the background model was complete. They ask whether the result could have appeared by chance. That last possibility is especially important. When researchers search through vast datasets, chance has many opportunities to arrange itself into something suggestive. A random cluster of events may appear in one part of the data. A small excess may rise above expectation. A curve may show a feature that looks meaningful. But if enough measurements are made, some apparent patterns will happen simply because randomness is not perfectly smooth. The human mind is built to notice patterns. Physics is built to ask whether the patterns are real. A statistical fluctuation can be exciting for a short time. It can create a question, attract attention, and guide further investigation. But it is not a discovery. A real signal should become clearer as more data is collected. It should sharpen, not fade. It should appear in the right places and not in the wrong ones. It should survive when the analysis changes. It should be visible to independent groups, using independent methods, under conditions that reduce the chance of shared error. Until then, it remains a possibility, not a fact. This caution can feel frustrating. It slows the story down. It resists the drama of immediate revelation. But that slowness is one of science's greatest strengths. If every anomaly were accepted as truth, physics would become a museum of false particles, imaginary forces, and beautiful ideas that nature never actually used. The point of skepticism is not to kill discovery. It is to make sure discovery means something. A particle that could change everything must survive skepticism before it becomes discovery. That sentence is at the heart of scientific trust, because the claim is enormous. A new particle beyond the standard model could suggest a hidden force, a dark matter connection, a new field, or a deeper structure beneath ordinary matter. It could change how physicists understand the early universe. It could open a new chapter in fundamental science. But the larger the implication, the stronger the evidence must be. Excitement is not enough. Elegance is not enough. A theory that feels profound is not enough. The signal has to remain. Some vanished signals are caused by detector effects. A detector is a physical object, and physical objects have imperfections. Sensors can respond differently under different conditions. Electronics can introduce noise. Materials can produce unexpected signals. Radiation from the environment can contaminate the data. Temperature, vibration, magnetic fields, and timing errors can all matter. The detector is trying to measure the universe, but it is also part of the universe. It has its own behavior, understanding that behavior is part of the experiment. Other vanished signals come from background noise. In particle physics, background does not mean unimportant. It means known or ordinary processes that can create events similar to the ones being searched for. These backgrounds can be extremely complex. A rare standard model process may mimic a new particle. A misidentified particle may create a false pattern. An ordinary interaction may appear unusual because part of the event escaped detection. Before scientists can claim something new, they have to understand what is old. That is often the hardest task. Known physics is not simple. The standard model can produce an enormous variety of events, and many of them are rare, messy, or difficult to model. Sometimes what looks like evidence for a new particle is actually evidence that an ordinary process was not understood well enough. That may be disappointing if one hoped for a revolution, but it is still progress. It sharpens the theory, it improves the experiment, it teaches scientists how nature behaves in difficult corners of the known map. A disappearing signal can still leave knowledge behind. It can reveal a flaw in the detector model. It can expose a background that needs better measurement. It can force more careful statistics. It can guide future searches away from false paths. Science does not only advance by confirming bold ideas, it also advances by eliminating them. There is dignity in that process. A false signal is not a scandal if it was handled honestly. It is part of the filtering system that separates reality from wishful thinking. The danger is not being wrong. The danger is refusing to find out whether we are wrong. Science earns credibility because it allows its most exciting claims to be tested, doubted, repeated, and, when necessary, abandoned. This is different from simple belief. Belief can attach itself to a beautiful answer and resist anything that threatens it. Science has to do the opposite. It must love the possibility of discovery while remaining willing to lose it. It must build instruments sensitive enough to notice the faintest clue and standards strict enough not to mistake noise for truth, sensitive enough to wonder, skeptical enough to trust. That balance is difficult, but essential. When a signal first appears, science may feel genuine excitement. They are human. They know what it would mean if the pattern were real. They know a new particle could open the door to dark matter, hidden sectors, or physics beyond the standard model. They know that a tiny anomaly could become a turning point in the history of science. But they also know how many hints have faded. So they wait, they test, they gather more data, they invite criticism, they compare independent analyses, they check whether the signal appears under different conditions. They ask the most uncomfortable questions because those questions are the path from possibility to knowledge. If the signal disappears, the universe has still answered. It has said, not there, not that particle, not that path. And that answer matters. It narrows the search. It cleans the map. It tells scientists which models are less likely, which backgrounds are more important, and which experimental methods need improvement. The absence of discovery is not emptiness. It is information, but if the signal does not disappear, the story changes. If it grows stronger with more data, if it survives every test, if independent experiments begin to see related evidence, then skepticism begins to transform. The very doubt that once threatened the discovery becomes the reason to believe it. The signal becomes credible, not because scientists wanted it, but because it remained after they tried to explain it away. That is, the moment a possible particle begins to become real. Not real in the sense that it suddenly starts existing. If it exists, it was always part of nature, but real in the scientific sense, established by evidence strong enough to enter the map of reality. This is why caution builds trust. A careful story is stronger than an exaggerated one. Saying we do not know yet is not weakness, it is honesty. Saying this could be new physics, but it might also be noise, is not less exciting. It is more faithful to how discovery actually happens. The universe is not obligated to confirm our hopes on the first attempt. It reveals itself through patterns that must be earned. A particle that could change everything must pass through doubt. It must survive background checks, statistical tests, repeated measurements, and independent confirmation. It must remain when the easy explanations are gone. Only then can it become more than a strange signal. Only then can it become a new ingredient of reality. And perhaps that is what makes the search so profound, at the edge of knowledge. Science does not move by certainty alone. It moves through disciplined uncertainty. It listens for faint signals, but refuses to worship them too early. It allows mystery to exist without forcing it into a conclusion. It understands that a disappearing signal is not the death of inquiry, but part of the way inquiry stays honest. If the signal fades, physics continues. If it survives, physics changes. Either way, the method remains, and that method, patient, skeptical, precise, and open to surprise, is why we can trust the moment when a tiny trace in the data finally becomes a discovery. The universe is not obligated to fit the theories humans have built for it. Our theories are maps. Some are rough sketches. Some are astonishingly precise. Some become so powerful that they feel almost like reality itself. But even the most successful theory is still a human structure, shaped from observation, mathematics, experiment, and imagination. It does not command nature. It follows nature as far as it can. The Standard Model is one of the greatest maps ever drawn. It describes the known particles of matter. It explains the forces that govern the microscopic world. Except gravity, it includes the fields and interactions that make atoms possible, that allow chemistry to exist, that give structure to the ordinary matter beneath planets, stars, oceans, and living bodies. It has predicted experimental results with extraordinary accuracy. It has survived decades of testing. It is not weak. It is not obsolete. It is one of the deepest achievements in science. But a map can be accurate and incomplete. A coastline can be drawn with precision, while the land beyond it remains unexplored. A theory can explain everything within its reach and still leave larger questions unanswered. The Standard Model gives us a remarkable description of ordinary matter, but the universe keeps pointing beyond it. Dark matter shapes galaxies, yet does not appear in the known particle catalogue. Dark energy influences the expansion of the cosmos, yet remains mysterious. Gravity bends space-time, yet still resists full union with quantum physics. Neutrinos behave in ways that hint at deeper mechanisms. Matter itself survived the early universe, for reasons the known theory does not fully explain. These are not signs that physics has failed. They are signs that reality is deeper than the current map. That is why a new particle would matter so much. It would not mean the universe is broken. It would not mean every successful equation must be thrown away. It would not erase atoms, chemistry, stars, or the technologies built from known physics. The world we understand would still remain real. But it would mean there is more. A particle outside the known catalogue would be a message from beyond the boundary. It could reveal a hidden field. It could point toward a new force. It could connect ordinary matter to dark matter. It could show that the visible universe is only one part of a larger structure. It could be a small clue to an enormous missing layer. The particle itself might be almost unimaginably subtle. A faint excess in data, a rare decay, a missing energy signature, a tiny disturbance in a detector buried deep beneath the Earth. It might not look like a doorway. It might look like a number that refuses to settle where the theory said it should. It might appear first as uncertainty, then as suspicion, then as evidence only after years of patient testing. But if it survives, it changes the meaning of the map, not by destroying the old one, by expanding it. This is how science grows. It does not usually advance by declaring everything before it false. Newton's laws were not useless after Einstein. Classical physics did not disappear after quantum mechanics. The older theories remained powerful within their domains, while the new theories revealed where the old ones ended. A new particle could do the same for the standard model. It could show that the known particles are the visible letters of a deeper alphabet. It could reveal that the forces we have named are not the full grammar of reality. It could suggest that matter, as familiar as it feels, is only the surface expression of fields and interactions still hidden from direct view. There is something humbling in this. Everything around us feels so complete. The ground seems solid. Light seems ordinary. Bodies feel physical and immediate. Stars appear as distant fires. The world seems made of things, arranged in space, governed by time. But beneath that everyday certainty, physics has already revealed layers of strangeness. Matter is not made from tiny solid objects in the simple way our senses suggest. Particles are excitations of fields. Empty space is not simply empty. Forces are expressions of deeper interactions, measurement, probability, symmetry, and information. All shape what reality becomes when we look closely enough. A new particle would remind us that this depth may not be finished. There may be fields we have not mapped, forces we have not detected, hidden sectors that barely speak to ordinary matter, particles that were abundant in the early universe but are almost invisible now. Rules that shaped galaxies before the first star ever formed. The universe may be full of structure that does not glow, does not touch us easily, and does not announce itself except through the faint pressure it places on our best theories. That is the strange beauty of fundamental physics. It teaches us that absence can be evidence. Missing energy can become a clue. Invisible mass can shape galaxies. A tiny asymmetry can explain why matter exists. A particle that vanishes instantly can reveal a field that fills space. The hidden world is not necessarily far away. It may be passing through us. It may be written into the vacuum. It may be buried in the early history of the cosmos. It may be waiting inside data we have not yet understood. If this particle is real, it may not simply add something new to physics. It may show that our deepest categories are incomplete. Matter Force, space, and time may not be the final foundations. They may be the visible expressions of deeper rules, deeper symmetries, deeper relationships still waiting to be discovered. That possibility should not make reality feel less real. It should make it feel more profound. The universe is not fragile because our theories change. It is not unstable because our maps improve. Reality remains what it is. What changes is our ability to describe it. What changes is the reach of human understanding. A new particle would not be a crack in reality. It would be a crack in our ignorance. And through that crack, a larger structure might become visible. Perhaps dark matter is not just invisible mass, but part of a hidden sector with its own particles and interactions. Perhaps the imbalance between matter and antimatter was shaped by particles that vanished long before stars existed. Perhaps gravity and quantum physics require a deeper connection than our current theories can express. Perhaps what we call empty space contains more structure than we know how to name. Each possibility is careful. None is guaranteed. Science does not move forward by believing the most exciting answer. It moves forward by testing the most precise questions. A signal must survive doubt. A particle must be confirmed. A theory must explain more than the mystery that inspired it. It must connect to evidence, make predictions, and withstand the slow pressure of experiment. But if the evidence holds, then the discovery would become part of reality's language. A new word, maybe a new grammar, maybe the first sentence from a hidden chapter of nature. That is why this search matters. It is not only about finding one more particle, it is about asking whether the universe we know is only the visible layer of something deeper. It is about whether the standard model, powerful as it is the final structure or only one floor in a much larger building. The answer may still be hidden. The signal may fade, the particle may not exist, or it may be waiting, quietly, inside a pattern too subtle to recognize at first. This is the edge where physics lives. Between confidence and humility, between what has been tested and what remains unknown, between the beautiful precision of the known map and the darkness beyond its borders. The universe does not owe us simplicity. It does not owe us completeness. It does not owe us a reality that fits inside the first theories we were clever enough to build. But it does leave clues in particles, in forces, in galaxies, in missing mass, in the early universe, in the smallest deviations from expectation, and perhaps in one tiny particle that refuses to fit. Nature may reveal that beneath matter, force, space, and time, reality still has hidden rules waiting to be discovered. Good night, and see you in the next video.